Hi, it is a review for exam number 2. Exam number 2 will cover sections 2.5 to 3.6. And you should understand all homework problems. Here are extra problems. Number 1, for what values of b is the function f continuous every year? Once x is less than or equal to 0, then it's a linear. As far as b is not minus 1, then it is well defined and linear. And the right side is quadratic. So both sides, the function is continuous. Now, once it is continuous at point 0, then it will be continuous every year. So we'll focus on continuity at 0. Okay, what is the definition of continuity at x equals 0? That is limit x approaches 0, f of x must be same as f at 0. Okay, here, first of all, we know that f at 0, okay, f at 0 is now, okay, x is less than or equal to 0. If x is 0, then the value must be minus b over b plus 1, okay? And of course, left-hand side is linear, so that limit of this function is the same as that. Now, limit from the right, limit x approaches 0 from the right of fx. That is, now x is larger than 0 and approaching 0, so that will become here 0 plus b, which is b. These two should be the same, then it is continuous. Okay, so here we can get minus b over b plus 1 equals same as b. Now, from this one, minus b equal now b times b plus 1, which is same as b squared plus b. And we are moving this onto the other side. Then we can get b squared plus 2b equal 0. Okay, so we can factor out b and b plus 2 equal 0. So here we have b equals 0 and minus 2. For these values, now the both sides will be the limit, and now the value over there will be the same, so that it will be continuous. So there are two values for b, 0 and minus 2. Of course, over there, the denominator is not 0, so that's okay. Now, limit involving infinity and asymptotes. Okay. Now, we have to find the limit x approaches plus minus infinity, x times sine 1 over x. If x becomes large or negatively large, then now that will become the infinity times, here now, 1 of x will become 0, so that sine 0 will be 0. So the infinite times 0 type of a problem. So we have to do some manipulation, okay, part A. And for this problem, now we may start with a change variable, t equal 1 over x. Then here, x approaches plus minus infinity is the same as now t approaches plus minus 0. Right? Okay, so we can say that, okay, it's approaching plus minus 0, so rather than equality. So here, approaching plus minus 0. So we can say that t approaches 0. So here, given problem, given term, change it into limit, and t approaches 0, and x will be 1 over t, and sine 1 over x will be sine of t. We already know that sine t over t as t approaches 0 is 1. So that 1 is the final answer for the problem. And that means that here the limit is 1. So here, now as x approaches minus infinity to infinity, so that here y equal 1 would be the horizontal asymptote. Okay. Now, part B, we want to find all possible asymptotes of the curve. Okay. Here is one order, the numerator is one order higher than the denominator. So that if you are making the practical division, then linear term plus remainder will be obtained. So here, y equal, rather than practical division, let's try to do this way. X squared minus 2x is same as now plus 1 and minus 1 divided by x minus 1. That is same as, now for these three terms, that is x minus 1 squared minus 1 divided by x minus 1. So that is same as x minus 1 and minus 1 over x minus 1. As x approaches infinity or minus infinity, that will become 0, approaching 0, so that is now oblique here asymptote. So we can say from this one, y equal x minus 1 is oblique asymptote. Okay. Now here, and when x equal 1, the value is blowing up, so that, and we can easily see that x equal 1 is vertical asymptote. So let's see here now, x equal 1 is vertical asymptote. To see the detail, let's try to sketch the graph of the curve. Okay. Now here, there is x-axis and there is y-axis. Okay, that is y. And the denominator is 0, x squared minus 2x equals 0. I mean, numerator is 0 when x equals 0 and 2. That means that it is passing this point and now that point, that is 2. And when x equals 1, then the function value becomes infinity. Here, we have 1 now here. Okay. Now, x is approaching to 1 from the left. Then, now this term, that one, and top will become here, and then y is approaching, the numerator is 1. As x approaches 1, then this value is 1 minus 2, which is minus 1. And now x is less than 1, so that x minus 1 is less than 0, but approaching 0, which means that there is 0 minus, and the value will be positive and becoming larger, 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 so that it's infinity. So here, x is approaching from the left, then value will go to infinity. And now, as x becomes large or small, then it is following this oblique asymptote. And so here, in going infinity and passing this point, so that it's going down and passing this point, and then approaching that oblique asymptote. Okay. How about x is approaching from 1 from the right, then here y will approach Okay, top will be minus 1, the same. The bottom here, x minus 1, x is larger than 1 and approaching 1. So x minus 1 is larger than 0, but becoming 0. Okay, so here, so that is 0 plus, whole thing is negative, but becoming large in magnitude, which means it is approaching minus infinity. So that as x approaches from the right, the value will go down minus infinity. So start with here, but the curve will pass this point. Okay, start with here and pass this point, but as x becomes large, then it is approaching the oblique asymptote. So that is a sketch of the function. Okay, now tangent lines and the derivative at a point. Okay, here fx is defined in this way. Once x is non-zero, then there's x squared, the sine 1 over x, and when x equals 0, the value is 0. Okay, first question is f continuous at x equals 0? Okay, we have to use the definition. Limit x approaches 0, fx must be same as f at 0. And here, that's defined to be 0. Now, at x equals 0, the value is 0. So that is, f of 0 is defined. Now, we have to find the limit, speed 0. But here, limit x approaches 0, f of x. Now, x is not 0, but becoming 0, approach 0, so that is same as limit x approaches 0, x squared sine, now 1 over x. Okay. Here, 1 over x, as x approaches 0, that one will be oscillatory. However, the value will be between minus 1 and 1. Now, this x will approach 0, so the x squared will approach 0 quadratically, rapidly, so that whole this multiplication will approach 0, so that limit is 0. So here, limit exists, and f is defined at 0, and the values are the same, so that it is continuous at 0. How about part B? Does f prime at 0 exist? And once it is continuous, then we can check the existence of derivative. Okay, f prime 0, that is basically, in definition, h approaches 0, f of h minus f of 0 divided by h. Once the limit exists, then we can say f prime at 0 exists. Okay, let's try to continue here. F of h, which is the same as now f of h, that is same as h squared, and sine, and 1 over h. F of 0 is 0 divided by h. Okay, that will be same as now limit, the same limit, h will be cancelled, we ignore this portion, so that the same as h times your sine 1 over h. Now again, this sine 1 over h as h approaches 0 will oscillatory. However, it's between minus 1 and 1. Now h becomes approaching 0, so that the multiplication will approach 0, so that limit exists, so it is 0. Now here, and f prime at 0 exists, so that we can find the tangent line, and as at the origin, and the slope is 0, so that part C here, the tangent line will be y equal 0. Okay. Okay, here, and we'll use the definition of derivative to determine if the piecewise defined function is differentiable at the origin. If it is differentiable, then what is f prime of 0? Okay. Now, for that, and first of all, here, if x is approaching from the left, then it is approaching 1. And also, from the right, x approaching 0, then again, it becomes 1. So we know that from the beginning is continuous. Okay? At least it must be continuous. Without continuity, you cannot get a derivative. Now here, in definition, derivative is at 0 is given in this way. F prime 0 is same as limit, and h approaches 0, f of h minus f of 0 divided by here h. Of course, the limit should exist. Then we can say here now the f prime at 0 exists. So that question is, does it exist? That is question. Okay. Now also we have to measure the limit and the both sides. So here, let's try to check both sides. And first here, limit, h approaches 0 from the left, and now f of h minus f of 0 divided by here h. Okay, this quotient is same as x is now, h is smaller than 0 and approaching 0. So when h is smaller than 0, then the first one, h plus 1, the top one will be used, and f at 0 is 1 divided by h. So that quantity is always same as 1, so that, okay, we'll make here now parentheses, so that limit will be 1. How about the other side? Here, limit h approaches 0 from the right, and here the quotient, that one, is the same as, now h is larger than 0, approaching 0, so that we have to use this one, that is square root of h plus 1. Now, f of 0 is the same as 1 and h. Here, as h approaches 0, now the numerator and denominator simultaneously approaching 0. So here, we can use the rationalization. We multiply the conjugate of this top, both sides. Then top will be changed into h plus 1 minus 1. Bottom will be changed into h times the conjugate, square root of h plus 1 plus 1. Okay. So h can be cancelled out, and 1 over here, square root of h plus 1 plus 1. Okay. As h approaches 0 from the right, and the value will approach here 1 over 1 plus 1, which is same as 1 over 2. So left limit of the quotient and right limit of the quotient are different, so that it's not differentiable at the origin. Okay. Here, we'll use differentiation rules, and especially product rule and quotient rule and so on. And we'll try to find here an equation of tangent line to the curve, okay, at given point. So we have to find the slope. A point is given, and through differentiation, we can find the slope. Y prime equal, by using power rule, 2 times 3x squared minus 2, and here the square root of x can be written x to the 1/2 if you are making here derivative and apply the derivative, then half will come out, and x to the half minus 1 is minus 1/2. That can be written 1/2 square root of x. Right? So that the derivative of this term is same as 1/2 square root of x. And derivative of 1 will be 0. Okay, we can rewrite here 6x squared, and 2 and 2 will cancel out, and minus 1/square root of x. So here y prime at x equal 1, okay, here 1 is same as 6 minus 1, which is 5. That is slope. And by using slope pointer form, we can get here y minus y0 equal the slope and x minus x0, which is 1. So that is an equation of the tangent line. Okay, here we have to get here now derivative y prime. By using quotient rule, we can get it. So here bottom squared, so it's x squared plus e to the x squared, and now top derivative. So we may consider derivative of x e to the x first, separately. Then the same as now by using product rule, it becomes 2x and plus x, e to the x, and now x e to the x. Okay, so that is x plus 1 and e to the x. Okay, so here now bottom squared, and derivative of this one, of course derivative of 2 will be 0, and derivative of this one will be here x plus 1 and e to the x, and times the bottom, which is x squared plus e to the x, and minus the top here 2 plus x e to the x, and then times derivative of bottom, which is same as 2x and e to the x. Derivative of e to the x is the same as e to the x. Okay, we have that derivative, and when x equals 0, y is 2, so we have to evaluate this slope along with x equals 0. So that, and here we have, okay, if x is 0, then that will be 1. The first term is 1, the second term will be 1, third term over there will be 0 plus 1, which is 1, minus, and that is here 2 times, okay, 2 plus 0, and 0 plus 1, 1, and the bottom, there is 0 plus 1 squared. So the top is minus 1, and bottom is 1, so the slope is minus 1. So here we have an equation of the tangent line y minus y0 equal the slope times x minus x0, which is 0. So you can simplify this equation. Okay. Okay. Number 6 is about the body moving along a line, and the S is the position is given in this way, and here we have to find the body acceleration in part A. Each time the velocity is 0, so that after making derivative, you can find the moment, the time when the velocity is 0, and by using the time you can measure the acceleration, which is a second derivative of this position. And this one is already in lecture note, so that try to see the video clip or your lecture note and try to understand it. Okay, so do it yourself. Okay, now number 7 here, and trigonometric functions. Is there constant a and b that will make this function g of x continuous at 0 and differentiable at 0, and try to give reasons for your answers. Okay, yeah. Now let's check the continuity first and then differentiability. Okay, for number 1, yeah, continuity means that now again we consider definition limit x approaches 0, g of x must be same as g at 0. So right now here g at 0 is defined, okay, x is larger than equal to 0. So once x equals 0, then now that is 0. Okay, that is 0. Now plus again 0. Right? So that that is 0. Now here right side is continuous and around 0, and then left hand side, now as x approaches 0, the value must be 0. Okay, so here limit x approaches 0 from the left and g of x, which is same as a limit, and x is less than 0, so that is same as now x e to the x plus ax plus b. So here this term will be 0, that term will be 0, so the limit part is b. That means that for continuity b must be 0, so we reach at that one. Okay, now second part. Okay, the differentiable means that now left hand side and it's differentiable as x e to the x and ax linear term and exponential term, and so that left hand side is differentiable, and also right hand side here that is sec is 1 over cosine x, so that at least in small interval it is differentiable. Here you can use for example definition differentiability that is the same as, for example, limit h approaches 0 and g of x minus g of 0 over h. So that here h is approaching, basically h is approaching from 0 minus and h is approaching 0 plus, and then the limit of the quotient must be the same. If you try to do this way, then already these functions are so complicated. So rather than doing this way, we'll try to consider in this way. Okay. Now, G is defined piecewisely, so that here, and look at in this way here. Now, in less than 0 is defined one way, and now here in x is larger than 0, it is defined another way. So we try to find here derivative from both sides, and then after taking derivative, we try to consider now the limit as x approaches 0. Then the both sides, the limit must be the same. If not, then here at 0 we may have a cursor, and this side limit and that side limit are different than cursor. So originally the derivative doesn't exist. So that now we try to get here g prime this side and g prime that side and approaching 0 from both sides, then the value must be the same. We'll use that the the geometric the knowledge to get here to decide A eventually. Okay, here, so we'll make a derivative. Okay, so here G prime, that is, for left hand side, that is same as x e to the x is same as x plus 1 e to the x, and derivative, and plus a. That is when x is negative. Okay, on right side, we are making derivative, then there is cosine x, sine, derivative of sine is cosine x. Now by using product rule, that is here sec x plus x times derivative of sec as sec x and tangent x when x is now larger than or equal to 0. So that now we try to apply limit as x approaches 0. Then, okay, from here, now as x approaches 0, then that'll be, of course, here approach 0 from the left. So that anyway, once it becomes 0, then it's 1 plus a. Now that'll become 1 plus a. How about the other side? That is 1. Now here again, this is 1. So that 1 plus 1. Now because of this term and these bounded terms, and of course tangent x also will approach 0, so that that will be 0. So this is two should be the same, which means that here a equal 1. So we found here b equals 0 and a equal 1. Also, these are reasons for the answer. Okay, here we have a final problem. By using chain rule, we'll try to get second derivative of the functions. Okay, here. And y prime first, that is same as, okay, momentarily you are thinking x squared as a variable u, then the derivative with respect to u will be e to the u, which is x squared, and now u derivative with respect to x, which is 2x. Okay, plus, yeah, that is 5 times now 2x. So we can rewrite here twice of x and e to the x squared plus 10x. Right? Now how about y double prime? One more time of derivative. Okay, here we have now, okay, that is, first we are making derivative for that one. There's x, okay, there's 2 and e to the x squared, and plus here 2x. Now derivative of this term, already we know that is the same as this one, which is now 2x e to the x. Okay. Now, and plus the derivative of 10x will be 10. So, okay, this e to the x squared. Okay. So that is same as now, okay, here, is the same as, that is 2 plus 4x squared and e to the x squared and constant term 10. So that is the final answer, second derivative of y. Okay, for that one. Okay, here, the same way, first we apply the one derivative, then there's a 9, and here x over 3 is a variable u, then tangent to u derivative is same as now sec squared u x over 3, and derivative of u with respect to x is same as 1 over 3. Right? So that is same as 3 times sec squared x over 3. Okay, we got the first derivative, and we'll do one more derivative, y double prime. Okay, that is now 3. And here we are considering sec x over 3 as a variable. Then that is same as now u squared. So that u derivative of u squared is same as twice of u. That is a sec x over 3. And we have to put here now sec x over 3 and prime x derivative. Okay. Now to get x derivative of this one, now x over 3 can be considered as a variable u, and so that sec u derivative will be here sec u x over 3 times tangent and here u, and here again u x derivative, which is 1 over 3. Okay. So yeah, 1 over 3 and 3 cancel out, and the coefficients are 2, and we have basically one sec x over 3 and another one, so that there's a sec squared x over 3, and we have one more here, tangent x over 3. Okay. We considered everything. Okay, so that is a final answer for y double prime. Okay, this is the end of a review for exam number 2. Thank you.